In this tutorial, we will show how ETABS can automate the application of post-tensioning in a slab to balance a portion of the self-weight. In this case, our target will be 60 to 80% of the self-weight. The floor plate is from a residential structure 8 stories tall with bays varying in width from 18 feet to 20 feet, consisting of 6-inch thick post-tension slabs supported by beams, columns, and core walls, all constructed of 5,000 psi concrete. We will run banded tendons in the X direction and distributed tendons in the Y direction. We start by verifying our material properties. We have a material for the mild rebar, our tendons, and the concrete. For our pre-stressing tendons, we will use the default A416 grade 270 steel. Next, we can verify our slab property. Note that it uses the 5,000 psi concrete and that the thickness is 6 inches. The tendons are made up of half-inch diameter strands with an area of 0.153 inches squared. Next, we will define the load patterns. 2 default load patterns are defined: dead weight with a self-weight multiplier of 1 and a live load with no self-weight. We will add a superimposed dead load for additional loads such as HVAC and non-structural walls. Note that we could also add a PT final pattern, which is for the application of post-tensioning forces on the model after all losses have occurred, and a PT transfer pattern for the application of PT forces prior to the occurrence of long-term losses. However, these will automatically be created by the program when we add tendons, so we do not need to add them at this time. Next, we will assign the floor loads. For this example, we are going to post-tension a single typical floor, and we will use floor 7. Floors 7 and below are similar. We switch our selection option to similar stories, so that when we assign loads to the 7th floor, the same loads will be applied to all of the floors below. We click on the 7th floor in the plan view, and note that 7 shells are selected. And we go to the Assign Shell Loads Uniform command. The dead pattern will be just for self-weight, so we switch to the live pattern and assign a load of 40 pounds per square foot. It will be in the gravity direction. We click Apply. With the form still open, click the previous selection button, switch to SDEAD, and assign a load of 25 pounds per square foot. And then click OK. We will change back to 1 story now, since we are going to perform the rest of the design on just the 7th floor. As a general rule, it is a good idea to include P-delta effects in our analysis, so we will specify that now. We are going to use an iterative method based on a combination of our gravity loads. In this case, we will use the dead loads plus a fraction of the live load. Next, we can start to lay out the post-tensioning. ETABS offers two ways to add post-tensioning to the model. One way is to draw the tendons, and this is done just like any other line type object. When tendons are added by drawing, we must explicitly input the number of strands and hence the force we want in the tendons. Now we select the tendon, and with the tendon selected, we can assign the number of strands, the tendon jacking stress, which end to jack from, and specify the losses. Losses may be defined in terms of percentage or by inputting detailed values for short and long-term losses. But we will define the losses in this example based on a fixed stress loss, 27 KSI at stressing and 13.5 KSI for long-term losses. This gives a total loss of 40.5 KSI. However, we are going to delete the tendon just drawn because in this model we are going to use the automated tendon layout option ETABS provides, whereby the number of strands and tendon profiles are automatically determined by the program to balance a percentage of the self-weight. With this option, tendons are added to design strips that we will create. To add the design strips, again, we may draw them like other line type objects, including specifying values using a properties of object box. And we have the ability to right-click on the strip, which brings up the strip object information form. However, ETABS also provides an automated scheme for design strip layout. And this can be found under the Edit menu. We will specify the layout for our typical floor, floor 7, and the strips will be added along the grid lines. Because we are using the strips for defining our tendon layout, we will not check the Include Middle Strips option. The first strips will be added in the X direction for layer A. These will be our strips for the banded tendons. Typically, there are two principal layer directions, and we will let the program automatically determine the strip widths. Now we will add the design strips in the Y direction, which will be layer B, and will be used for the distributed tendons. Note that a few of the design strips were drawn past the edge of the slab due to the fact that they were generated from the grid lines. We will delete these few and redraw them so that they lie within the slab. Start with those that are in the layer A direction. We do not need to worry about width, as we will adjust that in a moment. Next, add the strips in the layer B direction. Next, we will select all of the design strips. The status bar should show 13. And we will use the Edit Strip Width command to make sure that they are all set to auto. Since we are adding post-tensioning to a single floor for this example, we will set our 3D display to show only that floor, floor 7. And we'll turn off the grids to make it easier to see. We are now ready to have ETABS determine the post-tensioning needed in our design strips to balance a percentage of the self-weight. We will go back and select the design strips in layer A, and then go to the Add Tendons in Strips command. Remember that the tendons in the layer A or X direction are to be banded. An ending bandwidth may be specified by the user, but for this model we are going to specify 0, which will result in the program simply reporting the total number of strands required. For the banded tendons, we will use a parabolic shape and verify that the maximum and minimum balancing ratios are 0.8 to 0.6. By adding the tendons to the design strips, rather than individually drawing them, the program will automatically determine the number of strands and the vertical profile needed to balance the percentage of self-weight specified here. To review the tendons generated by the program, hold down the Control key and right-click on a banded tendon to display a selection list. This form shows that multiple objects exist at the same location. Select the tendon object and click OK. A tendon object information form is now displayed with 3 tabs. Click on the Assignments tab, and the number of strands required in this banded region, in this case 11, is displayed. Also note that it is unbonded. Click on the Loads tab, and we see that the tendon is stressed from the JN with a jacking stress of 216 KSI, that the loss at stressing is 27 KSI, and that the long-term loss is 13.5 KSI. On the Geometry tab, if we click in an Edit box, we can view the vertical profile. This tendon is broken up into 4 spans, with the profile type of parabola, which is what we assigned. Span profile information is displayed in the table, including the span length, the distances A, B, and C, and the distances from the bottom of the slab to the tendon at the left, intermediate, and right ends. The heights are governed by the values specified in the Tendon Editing Options area. Profile can be edited by typing values into the table or by grabbing the control points and moving them. We can also remove a support by selecting a span, note the color change, and clicking the Delete Support button. We can increase the vertical scale for better viewing, but can always reset the profile to the default settings if we do not wish to keep our changes. Now we will select the design strips in layer B. These will be used for defining the distributed tendons. Again, we add tendons to the design strips. But this time the tendons will be distributed with a spacing of approximately 36 inches on center. And they will have a shape of reverse parabola. We will use the same balancing ratio target. Note that a few of the tendons are missing. We can easily add these in by selecting a similar tendon and replicating where missing. We can also similarly edit those that extend past the slab by deleting and then replicating. If we control right-click on a distributed tendon and then go to the Assignments tab, we see that the program has calculated 2 strands per tendon, or roughly a bit more than 17 kips per linear foot. For the profile, note how the support points of the tendons are at the banded tendon locations, and note that the anchorage and stressing ends are illustrated by different icons. If we select a tendon once more and go to the Add Edit Tendons command, we can see some of the other editing options available. For instance, although all of the tendons in this model have been straight in plan, they may have other layouts. They may be circular or have multilinear tendons, as well as other curve types. We can also copy the profile from one tendon and paste it onto another tendon, useful if you have made adjustments to a profile and wish to use it in other locations. We have now generated a complete set of banded and distributed tendons for our typical floor. A quick check of the load patterns shows that PT Final and PT Transfer have automatically been created by the program when we added the post-tensioning. Now we may start the analysis. We will shut off the modal analysis case as we are not doing any dynamic analysis. Once the analysis is complete, the deformed shape for the dead load case appears. With the analysis complete, we will review the design preferences for the bonded mild reinforcement required in addition to the post-tensioning. We are going to use the ACI 31814 code. On the Cover tab, note the clear cover, and for this slab we are going to switch the preferred bar size to number 5s. This is the bar size the program will use when reporting reinforcing requirements. Note it changes to red to indicate the value has been altered. Also note that layer B will be the inner layer of the reinforcing. On the PT Stress Check tab, we can also review the preferences used for the PT. Note the strength ratio at transfer. When performing concrete slab design in ETABS, the user must explicitly select which stories should be designed. In this case, we will design only story 7, our typical floor. We are now ready to start the design using the concrete slab design command. We can view the slab design information by going to the Display Flexural Design command. We will use the strip-based design, and for display type, because we have post-tensioning in the model, we have a number of choices. In addition to enveloping flexural reinforcing, which is the larger of the reinforcing calculated by the strength or stress designs, we have shear reinforcement, strength flexural reinforcement by itself, stress reinforcement by itself, and 3 levels of stress checks: transfer, normal, and long-term. We will start by displaying the enveloping flexural reinforcement. For layer A, just the top rebar, and we would like it to show us the number of rebar required. From this diagram, it appears that relatively little reinforcement is required to supplement the PT for strength or stress design. Going back to the display, this time switching to flexural stress check long-term, which is based on 2 combinations. We will display this for layer B in the compressive stress type. Moving the cursor over the design strips displays the stress check values. Lastly, we will review the design combinations automatically generated by the program. Note that combinations are generated for strength design as well as the stress check levels. If we show one of the combinations for the strength design, note that it includes a load case PT final HP, which includes the hyperstatic effects from the PT. Also note that the combinations for the long-term stress are as described previously when displaying the design results. As a final note, designers should account for the fact that post-tensioning in a slab will cause the slab to contract or shorten, which may result in cracking if the slab contraction is restrained by other building elements, such as walls, beams, and columns. This concludes this tutorial on the automated post-tensioning of slabs in ETABS.